Hello and welcome to this lesson on the derivatives of inverse trigonometric functions. So first of all, let's consider the following function. Y is equal to the inverse sine of x, which can also be written as y is equal to arc sine of x. Now my personal preference is to write it as the arc sine of x, because if you ever decide to put exponents on a sine function, positive or negative, this sine inverse with this -1 looking exponent can be confusing in that particular instance. So I have a tendency to use the arc sine notation. Alright, so this y is equal to the inverse sine of x. The output of an inverse sine function, well, the output is y, is an angle. So the output of an inverse trig function is always an angle. So the output of inverse sine is an angle y, such that if I take the sine of y, that'll give me x. So sine of y is equal to x. That means the same thing as y is equal to arc sine of x. Now from this equation, x equal to sine of y, I'm going to find dy dx. So taking the derivative of both sides of that equation using implicit differentiation, the derivative of x gives me a 1. The derivative of sine of y gives me cosine of y, and then taking the derivative of y gives me dy dx. Now taking this equation and solving it for dy dx, I'm going to divide both sides by cosine of y, and that'll give me dy dx is equal to 1 over the cosine of y. Now from here, we would like to rewrite this equation, this dy dx, as some sort of algebraic expression, some function where there's only x's on the right-hand side. So we're going to go back to this original equation. X is equal to the sine of y. So if we interpret that equation, y is an angle, such that if I do the sine of y, well, the sine of y is opposite over the hypotenuse, and that's also x, which gives me x over 1. So the sine of y is opposite over hypotenuse, which is the same as x over 1. If we start representing this as a right triangle, then that will give us the following. So the sine of this angle y is the opposite, which is x, over the hypotenuse, which is 1. Now, since we have a right triangle, and we're calling the opposite side x and the hypotenuse 1, we can use our Pythagorean theorem to generate an algebraic expression for the adjacent side. So, using our Pythagorean theorem, a squared plus b squared is equal to c squared. This gives me x squared plus b squared is equal to 1 squared, which is the same thing as x squared plus b squared is equal to 1. Subtracting x squared on both sides, this gives me b squared is equal to 1 minus x squared. And then if I take the square root of both sides, this gives me b is equal to the square root of 1 minus x squared. So now what we have is we have this triangle up here, where the adjacent side is the square root of 1 minus x squared, the opposite side is x, and the hypotenuse is 1. So when we go back to that derivative that we calculated, dy dx is 1 over cosine of y. Cosine of y is equal to the adjacent over the hypotenuse. So if I flip that, 1 over cosine is the hypotenuse over the adjacent. So it's going to be the hypotenuse, which is 1, over the adjacent, which is the square root of 1 minus x squared. So my dy dx becomes 1 over the square root of 1 minus x squared. So what we've basically done here is we've actually derived the formula for the derivative of arc sine. So if we take the derivative of the arc sine of x, that is going to equal 1 over the square root of 1 minus x squared. So we've actually proved that that is indeed the derivative of arc sine. Now, using a similar process, we could actually go through all these 6 inverse trig functions, arc cosine, arc tangent, and so forth. But from now, I'm just going to look at the derivative rules for them. Now, the derivative rules for our inverse trig functions. Now, just like regular trig functions, inverse trig functions can be container functions for the chain rule. So I'm going to let the letter u be some function of x. U is equal to f of x, and then du will be the derivative of that function. So my derivative rules for our 6 inverse trig functions. So the derivative of the arcsine of u, that's equal to 1 over the square root of 1 minus u squared, where u represents whatever's inside of that inverse trig function, and then times the derivative of whatever's inside that inverse trig function. So there's the derivative of arcsine. The derivative of arc cosine is almost exactly the same as arc sine. The only difference is the derivative of arc cosine is negative. So in reality, I remember these two sort of in pairs. The derivative of arc cosine is this fraction. The derivative of arc sine is 1 over the square root of 1 minus u squared times du. And then the derivative of arc cosine is that with a negative in front. Now let's take a look at the derivative of arctangent. So the derivative of arctangent of u, that's equal to 1 over 1 plus u squared, where u is the stuff that's inside the arctangent, and then times du, the derivative of the stuff inside of my arctangent. Arccotangent, well, that's going to be the derivative of arccotangent. That's going to be the same as the derivative of arctangent, just with a negative in front of it. So tangent and arctangent have their derivatives have the same relationship as the arcsine and arccosine derivatives. Taking a look at the derivative of arcsecant, the derivative of arcsecant is 1 over the absolute value of u, and again, u is the stuff that is inside my secant function, my arcsecant function, and then times the square root of u squared minus 1, and then all that's times the derivative of the stuff on the inside. So there's the derivative for arcsecant, and the derivative for arccosecant is the same, just with a negative in front. So those are the derivative rules for our 6 inverse trig functions. Let's take a look at some examples. So the first example here, I want to find the derivative of the following. F of x is equal to the arcsine of the square root of x. So the first thing I'm going to do is I'm going to take that square root and rewrite that as an x to the 1/2 exponent. So, rewriting my problem in a derivative-friendly format, taking my derivative, well, my derivative rule for my arcsine, that's going to be 1 over the square root of 1 minus the stuff inside my arcsine, the x to the 1/2 squared, and then that is times the derivative of the stuff on the inside. So bring down my exponent of 1/2 and then subtract 1 from the exponent. So 1/2 minus 1 gives me an x to the negative 1/2. And then from here, we simplify this. So this 1/2 x to the negative 1/2, that's going to be on top. The x to the 1/2 squared, that just becomes a plain old x. And since I have a 1/2 on top, that's the same as basically saying a 1 over 2. And then I still have my x to the negative 1/2. So I've simplified this a little bit. So my answer can be written a few different ways. I could write my answer as x to the negative 1/2 exponent over 2 times the square root of 1 minus x. Well, this could also be rewritten. Since this has a negative exponent, I could choose to bring it down to the bottom and make this as a 2 times x to the positive 1/2 exponent. So I could write it this way. An x to the 1/2 exponent is a square root, so this could be written this way. And then if you wanted to, since you have two square roots that are multiply, you could multiply stuff inside with stuff inside. So x times 1 gives me an x, and x times x gives me an x squared. So one of the things that makes some of these problems interesting is the wide variety in which you could write an answer to these. So I say, which one of these are correct? Well, they're all correct. There are many ways to write a correct answer to this particular problem. That's one of the things that happens in higher level mathematics is there's a lot of different ways to write a correct answer. All right, let's take a look at another example. So example number 2, I want to find the derivative of the following. So I have f of x is equal to arc cosine of 3x. So my solution, taking the derivative, I get the derivative f prime of x is equal to negative 1 over the square root of 1 minus the stuff that was inside the inverse trig function, so that's 3x squared, and then times the derivative of the stuff that was inside that function, which is going to be a 3. Simplifying this, 3x times 3x is a 9x squared, and then the 3 just goes up on top. Not a lot of different ways I can rewrite that answer. Let's take a look at a third example. So example number 3, I want to find the derivative of this. So I've got f of x is equal to arctangent of x over 4. So rewriting this problem, this gives me f of x is equal to arctangent of a 1/4 as a coefficient times x. Taking my derivative, well, using my derivative rule for arctangent, that's going to be 1 over 1 plus the thing inside of my arctangent, which was x over 4 squared, and then times the derivative of 1/4 x, which is going to be a 1/4. Simplifying this, x times x is x squared. 4 times 4 is 16. And then when I multiply this by the 1/4, 1 times 1 gives me a 1 on top, and then I've got a 4 multiplied by the bottom. When I distribute the 4 through, 4 times 1 is 4, and then 4 times the over 16. This 16 and that 4 reduces, leaving me with a 4 on the bottom. Now, a lot of times mathematicians do not like looking at fractions inside of fractions. So what I'm going to do here is multiply the numerator and the denominator by 4. So 1 times 4 gives me a 4, and in multiplying the bottom by 4, that gives me 4 times 4 is 16, and then 4 times this over 4 gives me an x squared. So the answer to this one, f prime of x, is going to be 4 over 16 plus x squared. So again, reason why I multiply top and bottom by 4 is to get rid of that fraction that was inside of the fraction. Let's take a look at another example. Example number 4. Oops. So I want to find the derivative of f of x is equal to arc cotangent of x cubed. So taking the derivative, well, arc cotangent, when I take the derivative, that becomes a negative 1 over 1 plus the stuff on the inside squared, so that's x cubed squared, and then times the derivative of the stuff inside. So that's going to be a 3x squared. Simplifying this one, well, an x cubed squared, something with an exponent in parentheses raised to an exponent, we multiply those, so that gives me an x to the 6th, and that 3x squared just goes on top. So not a lot of simplifying with this one. Let's take a look at another example. So here we have the derivative of arcsecant. So I've got f of x is equal to the arcsecant of 5x. So taking my derivative, f prime of x, that's going to equal 1 over, and it's the absolute value of the stuff that's inside the arcsecant. So I've got the absolute value of 5x times the square root of, well, that 5x squared minus 1, and then times the derivative of the stuff that's inside that arcsecant, which is a 5. All right, simplifying this 5 is going to move up on top. The 5x times a 5x, that becomes a 25x squared. And here, this absolute value, since 5 is a positive number, the absolute value of 5 is just a plain old 5. Now, I don't know if x is positive or negative, so it still has to stay inside the absolute value. And then finally, these 5's get to reduce. So that ends up giving me a 1 over the absolute value of x times the square root of 25x squared minus 1. So that's the derivative of the arcsine of 5x. All right, let's take a look at one final example. So we want to find the derivative of the arc cosecant of x squared. So taking the derivative, this ends up giving me, well, since this is a arc cosecant, I'm going to get a negative, and I have 1 over the absolute value of the stuff that's inside my arc cosecant. So it's absolute value of x squared, and then times the stuff that's inside my arc cosecant squared minus 1, and then times the derivative of that stuff inside, which gives me a 2x. All right, simplifying this, well, the 2x, that's going to move up to the top. An x squared, in parentheses square, that's going to become an x to the 4th. Now here, oops, I see an oops here. So what I should have had, and I will change these notes here later, this x squared, since an exponent of 2 is always positive, there's no need to have the absolute values. So the absolute values of x squared should just be a plain old x squared on the bottom. Actually, I can change this right now since I'm actually working in Word. So let's change this. Let's get over to my equation editor. And I can actually change this on the fly. So that should be an x squared. There we are. And then this 2 over x over the x squared, that's going to reduce, and that's going to leave me with a single x on the bottom. So my answer here is going to be, my answer here is going to be a negative of 2 over x times the square root of x to the 4th minus 1. All right, so thank you for watching this lesson, and I hope to see you next time.